Well, welcome to this video lecture on thermodynamic cycles and the second law. And we'll also be talking about an absolute temperature scale at the end of this lecture as well. Go ahead and take a look at your screen. You'll see a picture of a superfluid helium. So this liquid inside this container is called superfluid helium. It's helium gas that's been cooled down to near absolute zero temperature. It's just a couple degrees above absolute zero, and it turns into a liquid, but it's a liquid with very special properties. Now, most fluids that you deal with in engineering situations have some viscosity to them, and you may know that viscosity is really kind of a measure of the internal friction within that fluid, and that's caused by the molecular movement of the molecules in the fluid. So the molecules are moving around kind of randomly, and because of momentum exchange from molecules of higher velocity to molecules of lower velocity and back and forth, you actually get this kind of internal friction. It's a topic that's covered more in a fluid mechanics class, not in a thermodynamics class. But anyway, when you bring the temperature of that fluid down to very small values close to absolute zero, at least in helium, what happens is that molecular movement goes from being random to the molecules actually starting to move in phase with one another, or the atoms in the helium start to move in phase with one another. And when that occurs, the viscosity goes away. So superfluid helium actually has zero viscosity, which results in some very strange behavior. For example, if you stirred up that superfluid helium, it would just keep moving continuously. It wouldn't slow down or stop like a regular engineering fluid would. And in the picture here, what ends up happening is this superfluid helium goes up the sides of the container, presumably due to surface tension, then come around and drip off the bottom. And that'll just keep happening until the whole container actually empties out. The viscosity doesn't slow that process down. So it's very strange behavior, and I show it here just because it only occurs near absolute zero, and we're going to be talking about the absolute temperature scale later in today's lecture. So let's get started. The very beginning here is going to be a lot of review from the last video lecture, but it's for a purpose. Now, we were talking previously about power cycles and refrigeration or heat pump cycles. And we draw these in a very kind of general sense here, where we have a hot reservoir and a cold reservoir, and our system is in here. The system, we don't need to know what the details of the system are. Okay, so the system may be comprised of different kinds of working fluids. You may have heat exchangers, compressors, turbines, a variety of pieces of equipment in different orders and things like that. We don't need to know those details. Okay, the analysis we're going to do here is very general. We don't need to know any of the details of what's happening in the system. If we go ahead and apply the first law to a control volume surrounding the system, so we'll do that for both of these. For the power cycle over here on the left-hand side, well, first of all, before we do that, the first law for any cycle, the change in the total energy of the system within that cycle for over a cycle is equal to zero, right? That's this expression right here. And the reason it's zero is because the total energy is a property, and we know that if you start at a particular state and then go back around over a whole cycle and end up at that same state, the properties will all be the same. So you won't get any change in the properties as you return back to the same state. So over a cycle, the change in total energy is zero because we're coming right back to the same state. Properties are not path dependent. And so the change in total energy of the cycle is zero, and then this is the heat going into that system over the cycle minus the work done by the system over the cycle. Or we could also write it as plus the work done on the system over the cycle. The only difference here is the minus W by or the plus W on. It's whatever way you want to look at it. So for a power cycle, like what we have here on the left-hand side, change in total energy over the cycle is zero. The heat going into our system over the cycle would be the QH minus the QC, so that's right here, minus W by. So if we rearrange that, we'll get this expression. I'll highlight it in orange because we're going to refer back to it. So that just comes from the first law. You can do the same thing for the refrigeration or heat pump cycle. There, the heat coming into our system is going to be QC minus QH, so that's right here. And then here we have work being done on the system over the cycle. That's there. So we'll get this expression. Let me highlight it in green. So that's what we get from the first law. Again, this is just review. And we like to, we've defined measures of performance, thermodynamic performance for the heat, for the power and refrigeration and heat pump cycles. The reason we do these definitions of performance is because, number one, it allows us to calculate, or we could calculate what the best performance would be. Like in an ideal situation, what's the best thermal efficiency or the best coefficient of performance. And then it also allows us to compare real cycles to one another. So not only what's the best case scenario, like the frictionless, reversible case, but for a real cycle, what real, power cycles are more efficient than other real power cycles. So it gives us a way to compare things. So for a power cycle, we define a power cycle thermal efficiency in this way. It's the work we get out of the system over the cycle divided by the energy we have to put into it from the hot reservoir over the cycle. The reason we define it that way is because for a power cycle, what we want to maximize is the work we get out of it. That's the whole point of a power cycle. And the cost is the energy we have to put in to our system. This would be like the energy we get from burning a fuel, for example. So we want to minimize that. So that's why we define it in this way. And then if we make use of our first law expression for the work, that's this numerator here, we'll get that, and then we can rearrange it and get this expression right here. 1 minus QC over QH over the cycle. That's what we have for our thermal efficiency for that power cycle. Now, if you remember from the Kelvin-Planck statement of the first law, the Kelvin-Planck statement of the second law, we know that the QC can't be equal to 0 over a cycle, right? The QC has to be finite. And so with that in mind, when we look at our thermal efficiency in terms of the heat transfers, you see that QC can't be 0, so that the thermal efficiency is always going to have to be less than 1. So that's just one ramification of the second law of thermodynamics, is you can't have 100% efficient thermal efficiency. You can't take all the energy from your hot reservoir and just turn it all into work. It's just not possible. You can do a similar kind of analysis for refrigeration and a heat pump cycle. So let's start with the refrigeration cycle. There, the coefficient of performance is defined as QC over W on. So the QC is the energy we're getting out of the cold reservoir. For a refrigeration cycle, the cold reservoir would be like the interior of your refrigerator, or if it's like an air conditioner, it'd be the interior of your house. And you want to get that as cold as possible. So you want to maximize your QC, and you want to minimize the amount of work you have to do to make that happen. So that's why we have QC over W on here. And again, we can make use of the first law expression for the work, and then we'll end up with this expression here, just all in terms of the heat transfers. And then same sort of thing for the heat pump cycle, except there it's the coefficient of performance, it should be heat pump cycle. So that coefficient of performance is QH over W on. So for a heat pump, what we're trying to do is put as much energy into the hot reservoir as possible. So we're trying to maximize QH. So for example, a heat pump in your house, you're trying to get as much energy into your house. The house is the hot reservoir. Trying to maximize that. So you want to maximize QH and again, minimize the amount of work that you have to do to make that happen. So that'd be QH over W on. And again, we can make use of the first law expression there. So we get another expression for the coefficient of performance in terms of the heat transfers. And the coefficient of performance expression for the refrigeration cycle and heat pump cycles, they look similar, but they are different. Like in the denominator here, we have QH over QC minus 1. Here we have 1 minus QC over QH. So they are different. Now from the Clausius statement of the second law, we know that the work done on the cycle here can't be 0, right? If it was 0, then we would spontaneously be moving energy from the cold to the hot reservoir, and we can't do that. It's a violation of the Clausius statement of the second law. So since we know the work can't be 0, if you look at this part of the expressions for coefficients of performance, it means the denominator can't be 0, which means that coefficients of performance have to be finite. Okay, so again, the second law puts some limit on how big our coefficients of performance can be. Now we're going to actually have even more limits on the thermal efficiency and the coefficients of performance, and you'll see what those limits are kind of at the very end of this lecture and then definitely in the next lecture. So this is just, what we're showing now is just one limit, but it'll be even more restrictive in just a little bit. In fact, it'll be based on the temperatures of the reservoirs, so that's a little preview. Now, So what we talked about so far is kind of a rehash of what we talked about in the previous lecture. The second law corollaries, we talked about these in the previous lecture as well, but I'm going to spend a little more time on them here. So one corollary is that the thermal efficiency for an irreversible power cycle is going to be less than a reversible power cycle. And that's if they're operating between the same thermal reservoirs. What I mean by that is operating between the same hot and cold reservoirs. So if you have this picture, but the system is irreversible, it'll have a smaller thermal efficiency than this picture, but this being a reversible system. Okay. So reversible systems have the highest thermal efficiency as well as the highest coefficients of performance. And another important corollary is that any two reversible power cycles or any two refrigeration or heat pump cycles, if they're reversible, they'll have the same thermal efficiency or the same coefficients of performance. So it doesn't matter what the reversible system looks like, as long as it's reversible, it'll have the same thermal efficiency, the same coefficients of performance. So reversible systems have the best performance, and it doesn't matter what the details look like. If it's reversible, it'll have the same performance as another reversible system. So these are actually really important corollaries, and we'll make use of them in upcoming lectures, okay, and as well as at the very end of this lecture. So let me just spend a little more time proving these corollaries for the power cycle. So I'm going to just kind of prove the first and second corollaries. The third and fourth corollaries follow the same kinds of arguments, but I'm just not going to do it here for the sake of time. So the way we're going to prove it is we're going to develop a system here where we have a hot reservoir and a cold reservoir with two different systems in here. We'll have one with an irreversible system and one with a reversible system, okay? And for the irreversible system, we have some QH going into the system, QC coming out, and we're going to extract some work from it. It's a power cycle, so we're going to get some work out of it. The work coming out, I'll put a subscript I there to indicate it's the work coming out of that irreversible system. And the Q going into the cold reservoir, I'm going to put a QC sub I here to indicate that's the heat going into the cold reservoir from the irreversible cycle. Now I'm also going to have a reversible cycle here, and I'm going to design this reversible cycle so that I'm pulling the same QH out of the hot reservoir. So it's the same QH here. And then I'm going to extract some work out of that, and I'll call that W sub R for the amount of work I'm getting out of the reversible system. And then that'll also offload some energy into the cold reservoir, as we have to do from the second law, right? And then we'll call that QC comma R here for the energy being offloaded from the reversible cycle. Now the QCs are different between these two because just in general, because these cycles are not identical. One's irreversible, one's reversible. They could just generally be different, right? So from the first law, for example, the W by will be equal to, what was it, QH minus QC. And so QC in general would be QH minus W by. So you can see that QCI, just in general, could be different from QCR. Even though they have the same QH, they're just generally just different systems here. The I and R are just different systems, so they generally could be different. So these two could be different from one another. So in the next step, what I'm going to do is I'm going to now flip the reversible system, the reversible cycle here. That one I'm going to flip upside down, so we're going to follow the dashed lines now. Since it's reversible, I can just go operate it in the opposite direction to make it a refrigeration or heat pump cycle, right? So I'm going to pull the QCR out of the cold reservoir. I'll put some work into it. I have to do that from the Clausius statement of the second law. And then move the QH into the hot reservoir. Okay, so I'm going to do that now. Since it's reversible, no problem. It all looks the same. It's just in reverse direction. And now what I'm going to do is I'm going to choose a system that consists of the hot reservoir and my reversible and irreversible systems here. So it'll look like that. Okay, so now when I do that, the reason I've chosen that is because you'll see that for the hot reservoir, when I change the direction of my reversible cycle, you can see I'm putting QH into the hot reservoir, and then I'm also extracting QH into my irreversible system. So there's no net exchange of heat with the hot reservoir. So it's basically like the hot reservoir doesn't exist. And then the exchange of energy with the cold reservoir is going to be, I'm going to pull QCR out of it and then put QCI into it. So the net exchange out of it would be QCR minus QCI. And then the net work I get out of this dashed red line would be the W subscript I minus the W subscript R, because I'm putting work into it in the reversible cycle. So just to kind of clean that up a little bit, I've redrawn the picture right over here, where C means the combined cycle, so it's the irreversible and reversible cycles combined. There is no hot reservoir here because, again, I'm putting QH into the hot reservoir and pulling QH out, so it's like there's no hot reservoir at all. The net work I'm getting out will be the W subscript I minus the W subscript R that I'm putting into the reversible system. So that's the net work I'm getting out. And then the heat exchange with the cold reservoir will be the QC sub R minus QCI. So now when you look at this, we have a system interacting with a cold reservoir acting over a cycle, and we're getting some work out of it. So if you go back to the Kelvin-Planck statement of the second law, go back to the last lecture, you'll see that there was a statement for the Kelvin-Planck statement saying that the work done by a system, the net work done by a system over a cycle, must be less than zero if there are internal irreversibilities present, or equal to zero if there are no internal irreversibilities if you're dealing with a single reservoir. Okay, so that goes back to the last lecture. It's just another form for the Kelvin-Planck statement of the second law. So now in our case, we do have internal irreversibilities because we have our combined cycle has an irreversible component to it. So there are internal irreversibilities. So that means that this net work we're getting out of it must be less than zero. That's just coming straight from here. And if that's true, then that means that the work we get out of the irreversible cycle must be less than the work we're getting out of the reversible cycle. So the irreversible cycle gives us less work. And remember that the thermal efficiency is the work we get out divided by the QH that we put into it. Well, remember the QHs are the same for the reversible and irreversible cycles because we chose them to be that way. So the QH is the same, but the irreversible work is less. So that means that the thermal efficiency for the irreversible cycle must be less than the thermal efficiency for the reversible cycle. So that's just the proof for this first corollary. Okay. The second corollary, we can just use the same kind of situation, but what I'm going to do there is I'm going to make this, I'm going to get, instead of an irreversible cycle, I'm going to have two reversible cycles. So I'll call this one R1 and this one R2. And so the work that we get out of these, this will be R2 and this will be R1 here. So I'm just going here. I'm sorry, it's a little messy. But now that I'm dealing with two reversible cycles, then when I go to the Kelvin-Planck statement, it says that the net work over the cycle should be zero because there are no internal irreversibilities. So I need to change this from being less than zero to being equal to zero, which means that the work due to each of these systems, the R1 and the R2, will be identical to one another. And again, since I have the same work and I have the same QH, then that means the thermal efficiencies for each of the reversible cycles should be the same. So that proves that second corollary. That's the proof for both of those corollaries. And like I said, you could do the same sort of thing for the coefficients of performance. Now, you don't really need to know the details of this proof. You're not going to have to reprove it or anything like that in this course. But I just thought it was interesting to actually show you how these things are proved. And what I find really interesting about it is that if you look at these pictures, we're dealing with very general schematics here. Hot reservoir, cold reservoir system, some heat transfers, and some work. It's a very general kind of concept coupled with some very general statements of the second law, and from those general ideas we get some very powerful statements that we'll use later on, knowing that irreversible efficiencies are less than reversible efficiencies. So, and that it doesn't matter what the reversible systems look like, they all have the same performance. The nice thing about this is now we can say that, okay, when we analyze reversible systems, that's our maximum performance that we're going to get. We're not going to ever get any better than what we're going to get out of a reversible system. So now we're able to start talking about what is the maximum limit of performance for like a power cycle or refrigeration or heat pump cycle. That gives us like a goal. We have our real systems which do have irreversibilities, but we can at least compare them to that ideal reversible case and see how close we can get to that. Right? We know we'll never get better than the reversible case because that has the highest thermal efficiency, for example. And it doesn't matter what the reversible system looks like, it's always going to have the best performance. They're all the same if they're reversible. But it gives us a target that we can move toward and see what's the best case scenario we're going to get. Okay? And so it's this reversible thermal efficiency or reversible coefficient of performance that's going to be the best we can get. So it's a little more restrictive than what we had here, for example. Here, we just said that the thermal efficiency had to be less than 1. But really, our maximum thermal efficiency will be whatever the reversible thermal efficiency is for a particular power cycle. That's really our maximum. So it's more restrictive. Okay, so we're going to talk more about what that maximum thermal efficiency is a little bit at the end of this lecture, but for sure in the next lecture. Okay. So let's move on, and we're going to talk a bit about the absolute temperature scale. This is actually an important part for determining what that maximum thermal performance is. Okay, so we talk about temperature scales like degrees Celsius, Kelvin, degrees Fahrenheit, degrees Rankine, and we've talked about how Kelvin and degrees Rankine are absolute temperatures. Those temperatures are they come from an absolute temperature scale. And that temperature scale is defined thermodynamically. You don't have to rely on any substance. It doesn't have to be an ideal gas or water or anything like that. It's defined just kind of from the same arguments I just talked about a moment ago. And we can define a temperature scale using those thermodynamic arguments. So let me go ahead and do that here. So we know that the reversible cycle performance depends solely on the heat transfer from the thermal reservoirs, since all reversible cycle efficiencies are identical. So what that means is when we go back up here, we have here, for example, the thermal efficiency for a power cycle is based on 1 minus the QC over QH. So these are our heat transfers. And so if we have a reversible cycle, let me just write it down here. And I'm just going to use the thermal efficiency for a power cycle, just to make it easy. We know that that's going to look like this. And I'm going to drop the cycle subscript. Just all of this is over cycle. It's just inconvenient to write that down every time. So we know that the thermal efficiency for a reversible cycle is the maximum thermal efficiency you're going to get. And it doesn't matter what the reversible cycle looks like. It's always the same thermal efficiency, right? That comes from our second corollary here. All reversible cycles have the same thermal performance. So since they all have the same thermal performance, that means they all must have the same QC over QH, right? So it depends solely on the heat transfers from the thermal reservoirs because they're all the same, so they all have to have the same QC over QH, the same ratio. Now the QC over QH, the heat transfer, it's driven by the reservoir temperatures, right? The amount of heat transfer you get is dependent on the temperature of those reservoirs. And really, the reservoirs are only defined by their temperatures, right? So when we talk about a hot reservoir, the only defining characteristic a hot reservoir has is its temperature. Let's call it T sub H. Same thing with a cold reservoir. The only defining characteristic is its temperature, T sub C. Okay? So the heat transfer is driven solely by the reservoir temperatures. So that means that the QC over QH must be some function of TC over TH, since the heat transfers are driven just by the temperatures. And by the way, this is a dimensionless quantity, QC over QH, meaning that the units of QC and the units of QH are the same, so they cancel out. So if that's dimensionless, then it has to be a function of some dimensionless quantities as well. So like TC has the same units as TH. It makes sense. So the ratio of heat transfers for a reversible cycle, over the cycle, reversible system over the cycle, is a function of the temperatures of the two thermal reservoirs. Okay? And again, this is only for the reversible case, because the reversible case is only, they're all the same and they all are given by the QC over QH. Now, what we're going to do is, we don't know what that function is, right? We just don't know. What we're going to do is we're going to define a temperature scale. We're going to say that for the temperature scale we're interested in, we'll call it the Kelvin absolute temperature scale. We're going to define that function as just being a proportionality. So we're going to define QC over QH for a reversible cycle as being equal to TC over TH. So we're going to just make that function, we're defining it. We can make it anything we want, but we're just going to, for simplicity, let's just make them proportional to one another. So I could have defined it, instead of the Kelvin absolute temperature scale, I could make the Waskren absolute temperature scale and make QC over QH equal to TC over TH raised to the 5/2 power, for example. I could do that. I could define it that way. It would just, nobody would use it. It'd just be more complicated and harder to deal with, right? So we just define our temperature scale that we're going to use as looking like this. So that heat transfers for this reversible, the reversible part's very important here, are just this, they go in the same ratio as TC over TH, the temperatures of the cold and hot reservoirs. Now that gives us just a ratio. It doesn't really nail down how to get a temperature, just gives us the ratio of temperatures, but it doesn't nail down an actual temperature. So what we'll do is we'll anchor our temperature scale against some easily defined point, and that point we use is the triple point of water. So the triple point of water is where you have solid, liquid, and gaseous or vapor water all simultaneously, and that occurs at a well-defined temperature of 273.16 Kelvin in our absolute temperature scale. So with these two things right here, we've kind of nailed down our whole temperature scale. And this is the Kelvin temperature scale that we use all the time. Now, if we did a degrees Rankine temperature scale, we still have this ratio, but we'll define the triple point in our Rankine temperature scale as being, 459 point something degrees Rankine. It's still an absolute temperature scale, but it's just numerically looks different. So one interesting thing about this is if you look at it, remember in our Kelvin-Planck statement of the second law, QC can never be zero, right? And if that's the case, then that means TC can never be zero, which means we can never reach absolute zero. That would, if we reached absolute zero, it would be a violation of the second law of thermodynamics, so we can't do it. So that's, you've probably heard that before, that you can never get to absolute zero. Well, thermodynamically, we've just shown it here. It's not possible. Okay, so another interesting thing, kind of getting back to this maximum thermal performance. So since we've defined our temperature scale like this, then we could substitute in here. So this becomes TC over TH. So you can see that our thermal efficiency for our power cycle, if it's a reversible one, I'm gonna highlight the reversible because that's really important. Remember, this is the maximum efficiency that we can possibly get. It's going to be 1 minus the ratio of the temperature of the cold and hot reservoirs. So that is the maximum thermal efficiency we can get. It's much more restrictive than this one up here, right? We can see now that the maximum thermal efficiency we can get is based on that temperature, TC over TH. And you can do a similar thing for the coefficients of performance. And again, we know that thermodynamically we can't get to a thermal efficiency of 1, which again means TC can't be equal to 0, right? It would be a violation of the second law. And you can see here, for example, if you want to increase the maximum possible thermal efficiency you can get in an ideal case, a reversible case, then you would want to decrease Tc and increase Th. So you really want a hot reservoir. You want to burn fuels at very high temperatures, and you want your cold reservoir to be as cold as possible. That way you get the highest possible reversible thermal efficiency. Now, one thing I want to just emphasize again is that the thermal efficiency for an irreversible system, you can still calculate it using 1 minus QC over QH, but notice I'm not writing the subscript reversible. Here it's there, but you can still calculate the thermal efficiency using 1 minus QC over QH, whether it's reversible or irreversible. But that will be always less than the thermal efficiency for a reversible system, where the QC and QH are specifically for reversible systems. And then those can also be written as 1 minus Tc over Th. So notice that this is going to be less than 1 minus Tc over Th. Okay, so the Tc over Th expression is only for a reversible system. It's one that has no internal irreversibilities to it. If you have internal irreversibilities, then you cannot use that. That only holds if it's reversible. But you can still use 1 minus QC over QH. That you can use all the time. Okay, so we'll talk more about this in the next video lecture, but I just wanted to give you a little preview here. And so I think we've covered everything I wanted to in this particular lecture. So just to quickly recap, what we did is we talked about, again, just reviewed just some basic analysis for power cycles, refrigeration, and heat pump cycles, just to show that how we calculate the thermal efficiency in terms of the heat transfers, same with the coefficients of performance. We talked about the second law corollaries, and I proved a couple of them using some arguments based on some very simple pictures and some basic arguments. And then we talked about the absolute temperature scale, which relied on this corollary number 2, that the thermal efficiency is the same between any two reversible systems, and so that means that it's just a characteristic of the heat transfers between them. And from that we defined the Kelvin absolute temperature scale in this manner. And then we gave a little preview about how we can calculate the maximum efficiency for a power cycle, for example, based just on the temperatures of the cold and hot reservoirs, and we'll talk more about that next time. So we'll go ahead and end the video lecture there.